A shipping container just fell on this car's roof. On purpose? The roof didn't move. Somewhere in Germany, an engineering department just lost 30 years of bragging rights. For most of the last century, safety in the automotive world had a very specific address. Germany, Sweden, sometimes northern Italy. Mercedes-Benz built the reputation. Volvo turned it into a religion. Audi and BMW cashed in on the premium that came with it. The formula was simple and frankly, brilliant marketing. Run a controlled crash at a fixed speed, into a fixed barrier at a fixed angle, film the crumple zone folding exactly as engineered, print the star rating, and charge tens of thousands of euros for the peace of mind. It worked because nobody outside that circle could match the metallurgy, the tooling, or the decades of institutional crash data. That monopoly is now cracking, and not because a challenger played by the old rulebook better. It's cracking because a new generation of Chinese electric vehicles, led here by the Zeekr 8X, simply refused to play by it at all. Instead of another 40 Mbps frontal barrier test filmed in a sterile lab, the engineers behind this car built a gauntlet of scenarios that look more like disaster movie set pieces than certification paperwork. Tires launched downhill at a climbing SUV, a tire blown out on purpose at motorway speed in the rain, and the headline stunt. A loaded shipping container dropped from 3 meters straight onto the roof. The question worth sitting with isn't, did it survive? It's, why does surviving this even matter more than surviving a lab test? And that's where the real engineering story begins. Laboratory crash tests are static, predictable, and this is the uncomfortable part, largely known in advance by the people building the car. Engineers can tune a crumple zone, a pillar, or an airbag timing curve specifically around the exact speed and angle a regulator will use to test it. That's not cheating, it's just how certification has worked for decades. But real roads don't behave like a lab. Real roads throw combinations at you. Wet tarmac, a sudden crosswind, a tire that lets go without warning, all stacked on top of each other in the same 3 seconds. Take the uphill obstacle scenario as an example of why this distinction matters physically, not just rhetorically. A heavy SUV climbing a steep low-grip incline already has its weight shifted rearward. Ask the driver to swerve violently to dodge something rolling downhill, and a conventional passive suspension, a mechanical anti-roll bar, some fixed dampers, has no way to anticipate the load transfer. It can only react after the body has already started to lean. Weight piles onto the outer wheels, the inside tires lift, contact patches shrink, and traction control is left fighting a battle it was always going to lose. That's the mechanism behind a huge share of real-world SUV rollovers. Not one dramatic failure, but a chain of small, sequential losses of grip that a static crash rating never captures. The high-speed blowout scenario exposes an even sharper gap, a front tire disintegrating at 70-80 miles per hour in rain with a crosswind pushing sideways. That combination is close to statistically worst case for a conventional car. Standard electronic stability control reacts by braking individual wheels after it detects yaw, which on a wet, already compromised surface can make the spin worse rather than better. Most drivers in that situation don't get a second chance. Here's where the engineering genuinely diverges, not just in degree but in category. The Zeekr 8X isn't running a faster version of the same reactive hardware. It's running a predictive, electronically actuated suspension and drivetrain system that calculates yaw rate, steering angle, and chassis pitch before the body has physically started to roll. When the driver yanks the wheel to dodge an obstacle, actuators at each corner apply counterforce to the outer struts in milliseconds, fast enough that the car stays close to flat instead of leaning into the turn the way your instincts expect. Keep the vehicle flat, and you keep all 4 contact patches loaded evenly, which is exactly what the dual-motor all-wheel drive system needs to put power down without a wheel spinning uselessly in the air. The blowout recovery works on the same logic, applied to a different failure mode. Instead of relying primarily on braking, the car uses steer-by-wire, a steering system with no direct mechanical link between the wheel and the tires, combined with independent torque vectoring at each wheel. The moment tire pressure hits 0, sensors detect the sudden asymmetric drag and the resulting yaw almost instantly. Rather than braking the car into a wet, unstable stop, the system cuts power to the destroyed wheel and pushes extra torque to the opposite side, essentially using acceleration to pull the chassis straight instead of fighting it with brakes alone. Meanwhile, steer-by-wire makes thousands of tiny corrections a second without transmitting the violent kickback through the driver's hands. It's the difference between a car that reacts to a problem and a car that's already solving the equation before the driver has consciously registered anything went wrong. Then there's the container drop, which is really a metallurgy story more than a software one. Lab roof crush tests apply load slowly, through a hydraulic press, useful for measuring static strength, but nothing like the instantaneous energy transfer of several tons landing in a fraction of a second. Surviving that test intact comes down to gigacasting, replacing dozens of welded joints with single-cast aluminum sections, paired with hot-stamped boron steel with yield strengths in the thousands of megapascals, concentrated in the A, B, and C pillars. Preserving that survival cell isn't just about the cabin, either. It's what keeps the battery enclosure in the floor from deforming during a side impact or rollover, which is the difference between a bad accident and a thermal runaway fire. None of this makes European engineering incompetent. Mercedes, Volvo, and BMW still build genuinely capable structures, and decades of real-world crash data behind those brands are not nothing. What it exposes is complacency in the testing philosophy itself. If your entire safety narrative is built around passing a known static test, every engineering dollar eventually gets optimized toward that exact test, not toward the messier scenarios drivers actually encounter. Chinese manufacturers, entering the market with far less brand equity to protect and far more to prove, took the opposite bet. They built their credibility around scenarios nobody was ever required to survive on paper, and then filmed the results for millions of viewers instead of quietly filing them with a regulator. That's a fundamentally different incentive structure, and it's producing fundamentally different engineering priorities. Predictive control over reactive control, integrated software chassis systems over isolated mechanical components, and structural rigidity tuned around protecting a battery pack rather than just protecting a cabin. It also changes the economics of the entire segment. For decades, German engineering functioned almost like a luxury tax. Buyers paid a premium not just for comfort or badge prestige, but for a genuine, measurable safety advantage nobody else could replicate. Once a rival demonstrates on camera that the underlying advantage no longer holds, that premium becomes very difficult to justify to a rational buyer. Tesla faced a version of this shift with software and range years ago. Now the same disruption is arriving in structural and dynamic safety, arguably the last fortress the legacy brands had left to defend. There's also a manufacturing story hiding underneath the marketing footage. Gigacasting isn't just about strength. It collapses dozens of stamped, welded parts into a handful of cast sections, which cuts assembly complexity and cost at the same time it increases torsional rigidity. That's the rare kind of engineering shift that improves the product and the factory economics simultaneously, which is exactly why it's spreading so quickly across new EV platforms worldwide, including some Western ones now racing to license or replicate the process. The passive anti-roll bar reacting a half-second too late, the safety cage rated only for a press that moves at a fraction of real-world speed. That entire generation of thinking just got a very public expiration date. The Zeekr 8X isn't proof that Chinese cars are simply better. It's proof that an entire industry's definition of safe enough was quietly outdated, and somebody finally built a car willing to prove it on camera. The real question now isn't whether this technology is impressive. It's how long the legacy brands can keep charging a premium for a rulebook nobody's required to follow anymore.